Hello everyone, I'm here with another video on exponential growth. In the last video we had a look at what exponential growth is, and in this one we're going to see how we can turn that into an exponential formula. For that we will first have a look at an example of how a graph for this can look, and from that we will find the general form of the exponential formula. In the end, I will also take the opportunity to have a look at what happens when you do something to the power of 0, as exponential formulas give us a good way to find out. So let's start with an example. Let's say you are 8 meters away from something and every minute you halve that distance. So after 1 minute it's halved again, and every minute the distance becomes half. As you can already see, you get very close to a distance of 0, but you don't quite get there. Now this in itself is not yet the graph that we're looking for, because a graph is generally smooth. But if we take these points and we find the line that connects them, then we already have our graph for exponential growth. Now let's have a look at a table for that. So I put those halved distances in there, 8, 4, 2, 1, a half and a quarter. And we see that every step of the way we do times a half, obviously. So the growth factor is a half. So rather than making this graph, looking at the table, let's see what we can do using only this growth factor. We know that we start at a distance of 8 meters, 8, whatever. So after 1 minute, it is halved. It's 8 times a half, so 4. After 2 minutes, this number, 8 times a half, is halved again. So we get 8 times a half to get 2. But we can also shorten that. A half times a half is a half squared. So we get 8 times a half squared, which is 2. So we can continue this. After 3 minutes, 8 times a half times a half times a half. A half for each minute we spend, and we can shorten that as 8 times a half to the power of 3, which is 1, which we saw in the table earlier. That means that we can try to find a pattern in general for after t minutes. We saw that after 1 minute it's just 8 times a half. After 2 minutes it's 8 times a half to the power of 2. After 3 minutes, 8 times a half to the power of 3. So if we generalize that, we get 8 times a half to the power of t, no matter what amount of minutes we've got. From now on, I'm also going to use a slightly different notation because this gets confusing if we have variables with x. So instead of writing a cross for times, we will be using a dot for times. So you'll see that happening in the rest of the videos. Alright, so we have this one formula. Let's see how we can generalize this. So we had our d equals 8 times a half to the power of t. That's our one formula for this example. But what does that 8 mean? What does that half mean? How can we use this in general? Well, this 8 is the number we started with, the number we began with, the initial amount. So we get d equals the initial amount. And then this half is our growth factor. So we can have as a general formula d equals the initial amount times the growth factor to the power of t. And as we don't want to constantly write this out, we shorten that. Growth factor we write g. And initial amount, I'm sticking with what the book uses, which is a b for beginning amount. So d equals b times g to the power of t. B for beginning initial amount, g for growth factor. And that gives us our general formula for an exponential formula. Now back to our first example. As I said, exponential formulas give us a way to think about what happens with something to the power of 0. Now we know that at t equals 0, the distance is 8. So that means that apparently if I fill in t is 0 in my formula, 8 times a half to the power of 0, the answer is going to be 8. Now, if 8 times a half to the power of 0 is 8, then apparently this half to the power of 0 is 1. Because if 8 times something is 8, then that something must be 1. So half times to the power of 0 is 1. And this actually works in general. Anything to the power of 0 is going to be 1. This doesn't necessarily make sense if you think about what power means, but this is just an agreement that was made so that essentially these functions, these formulas, work nicely. So rather than specifically understanding what that something to the power of 0 is, it's something that you have to memorize because it's just something that's been agreed upon so that it works out nicely. So let's summarize. We first had a look at exponential formulas, and we saw that we could get that by doing d equals initial amount times the growth factor to the power of t. We usually use d and t as the variables. And we shorten that to d equals b times g to the power of t. And we also saw that we had a special case with powers of 0, that it doesn't matter what number you pick, but if you do it to the power of 0, it's going to be 1. So these two things summarize this video. In the next video, we will look further into what we can do with growth factors and how we can change our formulas depending on the situation.